going back to pre-industrial conditions, like the net zero politicians want to do, is a really bad idea, because we know what happens if we return to pre-industrial conditions. We get clobbered.
This is Climate Debrief, brought to you by the CO2 Coalition. I'm Angela Wheeler. In a moment, we'll be having a conversation with Dr. Koen Vogel, who earned his Ph.D. in geology from Penn State in 1991. Since retiring, he has returned to his early interest in climate change, particularly the melting of the last glacial ice sheets. So we asked him to do a short presentation on the subject. This slide shows a special wavelength analysis of summer sunlight reaching 65 degrees north over the last 800,000 years. What does this graph reveal, and why does it suggest that changes in solar insolation still can't explain what triggered the rapid end of the big ice ages every 100,000 years?
Okay, so I was questioning whether or not to put this slide in, because it's a fairly difficult plot to understand, and even for scientists. What this shows you is the previous solar insolation curve at 65 degrees north latitude, but then in the frequency domain, which is kind of hard to understand. But I'll try to explain with a simple example. If you've ever heard the Jaws theme song, it starts out like da-dum, and after 5 seconds, da-dum. And then, but after a while, the shark is getting closer, and it picks up speed, da 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 da, and it repeats itself every half second or so. If you would plot that Jaws theme song on a coherency plot, you would see a period of 5 seconds at the start of the song, which drops to a period of 0.5 seconds at the end of the song. So what this coherency plot represents, is the beat of the solar insolation. So what is pulsing? What is its pulse? You can see this is the Lasker data, which I've been showing in the past slides, but then in the frequency domain, you see there's on the right-hand side, the power of the different wavelets which it contains. And there's a big power spike at precession. So precession has a lot of power in the solar insolation. It varies the solar insolation a lot. And a minor peak at 41,000 years, which is obliquity, which has a lesser role, but still a significant role. And there's nothing at 100,000. There's absolutely nothing. There's nothing there. And you'll see several authors, and they get published in distinguished journals. They'll have some kind of slice and dice solution where they take a little bit of that, take from the bottom, add it to the top, and they'll come up with 100,000 year cycles. But either that's wrong, or Lasker is wrong, and Lasker is not wrong. So this is what goes into the climate models. This is the answer in the back of the book. Lasker solar insolation solution is what you put in your climate models. If it's not in Lasker et al., it doesn't exist. It's not an orbital forcing. You can juggle all you want, but if it's not in there, it's not in there. So this is basically the centerpiece of the puzzle that disproves that solar insolation has anything to do with the glacial melt.
Given your expertise, please tell our Climate Debrief viewers and listeners why solar insolation variations don't trigger deglaciations.
Well, there are several other major climatologists who weren't fans of the solar insolation solutions explaining the 100,000 year cycles. The main one being Milankovitch, who, the inventor of the cycles, who said, well, basically it doesn't work. Brook and Denton, who I've been quoting as well, recognize that there is some kind of orbital forcing happening, but not a conventional Milankovitch type forcing, a solar insolation forcing. So the bottom of the quote says, the glacial cycle cannot be explained by the conventional Milankovitch ice sheet link. It can't get clearer than that. They didn't believe there was a solar insolation solution. But they do recognize that it's orbitally forced. So it gives you a bit of a problem, what to do.
As shown in this graph, how is it possible that these two specific orbital changes can reconstruct the entire ice age pattern so well when the usual textbook explanations can't?
So this basically doesn't explain anything. It's just, it's my own personal graph. I've tried to reconstruct the ice volume graph using the orbital inclination cycle and an obliquity cycle. And you can see, you can get a fairly good match between the ice volumes using just combining the two orbital forcings, orbital inclination, which doesn't change solar insolation, and obliquity. And you can see that especially impressive are the sharp deglaciations happening, for example, the one around 400,000 years. Conversely, you can take the ice volume curve and extract from it the components, the 100,000 year cycle component and the 41,000 year cycle component, and what you'll get is obliquity and orbital inclination. Exactly that. There's no shifts or no anything, no magic involved. It proves beyond, there's a 1 in 100,000 chance that this is a coincidence. What is causing what is causing the deglaciations is cycles in orbital inclination and obliquity, and orbital inclination doesn't vary solar insolation at all. So it's a mystery.
Could an exploding comet deliver the kind of power you mentioned in the slide? And why do you think this might be the real trigger that suddenly ended the last ice age?
Well, the serious part of this presentation is more or less done. CO2 and solar insolation didn't do it. They were innocent bystanders. This is a theory that's been promoted on Netflix, and I need to set up the slide a bit. So if you've watched the series Ancient Apocalypse on Netflix, it combines three fairly low probability ideas proposed by Graham Hancock.
Well, I'm Graham Hancock. I don't claim to be an archaeologist or a scientist. I am a journalist, and the subject that I'm investigating is human prehistory.
Graham Hancock, by the way, I'm a fan of his work. I've read some of his books and I've watched the whole series, but some of his ideas are better than others. So he's combined three ideas in his Ancient Apocalypse series. First is sort of a red thread through all of his work, is that there was an ancient civilization, an advanced ancient civilization that met a catastrophe and somehow got lost in history. The second low probability item is that a comet struck Earth around the Younger Dryas. The theory is called the Younger Dryas impact hypothesis, and there's not much evidence that it actually happened. There's no meteorite impact hole or something which proves, credibly proves that it actually happened. And the last the item of what he combines is that this Younger Dryas comet hit the ice sheet, caused a massive flood, which then flooded the ancient, the advanced civilization and destroyed it. So he talks a bit during the series about Noah's flood and the Epic of Gilgamesh. Now Noah, Bible scholars think, lived about 3000 BC, so about 5,000 years ago. The Epic of Gilgamesh, a bit older, perhaps 6,000 years ago. The Younger Dryas happened 13,000 years ago, so 7,000 years before Noah's flood. So we're talking about something different than Noah's flood. What about Atlantis? That's the other thing which he likes to contemplate. Maybe it was Atlantis that was destroyed during the Younger Dryas. So if you're living in the Younger Dryas, you've seen quite a bit of sea level rise. You've seen the sea level rising about 40 meters over the last couple of millennia. It was rising at a rate of about 1 meter every 100 years. So Grandpa Joe's beach shack is now somewhere out in the bay. You would know that you shouldn't build on your beachfront property. You shouldn't build your house on the shore. You'd probably build it somewhere high up in the hills. For example, Athens and Rome, they're built far away from the sea, not because they're worried about comet impacts and glacial melt. It's because if you build too close to the shore, you might get hit by a storm surge. For example, New Orleans, during Hurricane Katrina, was hit by an 8-meter storm surge, which basically flooded out the town. So if we're talking about an advanced civilization, they would probably have built their cities, say, up a bit above sea level. say 15 meters above sea level doesn't sound too onerous. So what I'm doing here is calculating how much ice you need to melt to have a 20-meter sea level rise, instantaneous 20-meter sea level rise. So the ocean area is about 300,000 square kilometers. A 20-meter sea level rise is about 0.02 kilometers. So you're talking about 6 times 10 to the 6 cubic kilometers of water. And we'll have a bit of fun with scientific prefixes here. So 6 mega cubic kilometers of water is 6 peta cubic meters of water, 10 to the 15th, weighing 6 exakilograms, which is 6 zettagrams, 10 to the 21st grams of water. A lot. The numbers are getting bigger and bigger. Melting 6 zettagrams of water requires 334 joules per gram, which gives you a grand total of 22 joules of energy that you need to melt to cause a 20-meter sea level rise. That's a lot of energy. That's a million, billion, billion. The Chicxulub meteorite, the one that killed the dinosaurs, imparted a kinetic energy of about a seventh of that amount. So you need 7 very, very large meteorites to cause a 20-meter sea level rise. And they would leave an impact crater. There's no question that they could just sort of hit the ice and disappear. The Tunguska event, which was a meteorite impact in Siberia, which is often mentioned as maybe something like that happened, it exploded above the ice sheet and melted it, was about 10 to 20 megatons of TNT. You'd need several millions of Tunguska events all hitting at the same time to cause a 20-meter sea level rise. So it's not a credible theory. You need too much energy. But it's fun. I mean, I kind of hope that there would be a big meteorite impact, but it's just not credible.
So how did the big melt start before the climate changes?
So this is once again from the wonderful Anderson and Bournes there. Just hand drew it on there. If you imagine the climate systems that were happening back then, you'd have an ice cap climate over the North American ice sheet. Very, very cold, 20 to 30 degrees colder than today. It never gets above freezing. And it's very hard to get heat across the polar front. If you live in northern Canada, it doesn't often get very warm there. If you're behind the polar front, as sometimes happens when you get a polar vortex, it's pretty cold. So what we're presented with is really a big problem. How did we get the heat to the ice sheets? Now, what we do in geology is we try to look for present-day analogs. We look for a place where it's very cold and the ice sheets are melting. And the only place that really applies is Antarctica. It seldom gets above zero in Antarctica. And there's quite some melting going on in Antarctica. You just don't notice it. The 16th largest lake in area is called Lake Vostok, and it sits beneath the Antarctic ice sheet. Now, how does that happen? You have geothermal heat that comes from the ground, and it melts the basal parts of the ice sheet. And it can happen if that meltwater is sitting on a hill. The meltwater will flow downhill, and it takes its heat with it down to the lower parts of the glacier. And if the meltwater lubricates enough, then the ice sheet can start to glide over the basal meltwaters. It lubricates its movement and increases friction heat, which increases the meltwater even more. So it's sort of a positive feedback loop. Now, there is an ice sheet which is currently melting, which geodoc nature has said is caused by an increase in geothermal warmth. It's called the Thwaites Glacier. And while I don't want to quote alarmist literature, there's some people, some pundits in the press, who claim that it could be gone. The whole Thwaites Glacier could be gone in 200 years, and sea levels will rise 3 meters over these 200 years. So if you work out the average, it comes to about 1.5 meters per 100 years, which is the rate that we were talking about just now, was happening during the Younger Dryas, during a period of high melting. So what they've involuntarily proven is that you can use geothermal heat to melt a glacier and cause sea level rise of the same type that happened during the glacial melt. So there is geothermal melting happening in Antarctica, and if you look back 15,000 years ago at the North American ice sheet, which is on the left there, you see not a lot has changed. We're almost at the end of the climate change, and the ice sheet still looks more or less the same. There is one big feature which is different, and that's a corridor that's melted through the heart of the ice sheet. Now, solar insolation can't do that, and CO2 can't do that either. Neither a meteorite wouldn't be able to do that either. But the corridor follows a geothermal anomaly. You can see the C and E, Calgary, Edmonton, Y is Yellowknife. So all the way from Calgary up 2,000 kilometers to the north, a corridor was melting. And if it was solar insolation, you'd expect melting to start in the south. If it was CO2, you'd expect the whole thing to start melting, probably a bit more in the south than in the middle. A corridor, you can't melt it with CO2 or solar insolation. At the time of the melting, we did have a lot of volcanic activity in the area. So Mount St. Helens erupted 20,000 years ago and 19,000 years ago. Glacier Peak erupted around that time. Mount Hood erupted around 15,000 years ago. There was a lot of volcanic activity going on. So yeah, that's where I have to leave it, because that's where the trail of breadcrumbs sort of stops. The peer-reviewed trail of breadcrumbs doesn't go any further.
Can we expect another ice age? And if so, when?
Well, you saw the glacial volumes graph at the start, and glacials have been coming back regularly every 100,000 years. So can we expect another ice age? We'd be stupid not to, because history has proven that they come every 100,000 years. What I've done here is plot the current interglacial, the ice volumes of the current interglacial in blue, over the MS9 glacial volumes. Yikes! Right around this time, MS9 started reglaciating. So can we expect a glacial period? We might, but there's some climate modelers who, using the faulty climate models that can't predict deglaciation, predict that we've now have enough CO2 in the atmosphere that we don't have to be scared anymore about a new glacial period. But yeah, you're using climate models that can't predict the deglaciation, so it's a bit iffy. Going back to pre-industrial conditions, like the net zero politicians want to do, is a really bad idea, because we know what happens if we return to pre-glacial, pre-industrial conditions. We get clobbered. Every time the glaciers grew again was a time when the CO2 was about pre-industrial, 280 parts per million. So, yeah, it'd be kind of ironic if the politicians all of a sudden said, oh, guys, start using your gas guzzlers again because the glaciers are coming. Is 440 parts per million atmospheric CO2 enough to stop a glacier? Nobody really knows, because we don't have the climate models that can tell us that. What we do know is that we're kind of due at the moment, and we really need a climate model that can handle deglaciations, which is probably where I should end this, but I don't like leaving viewers hanging like this. So great, now we have glaciers to worry about as well. You'll notice the time scale on the bottom is thousands of years. So we're not going to see glaciers in Chicago again for quite a while. Our grandchildren, great-grandchildren will probably not see glaciers of any size in the near future. My personal work suggests that we're probably good for another 12,000 years, but that is just opinion. It's not peer-reviewed. It's just based on my own understanding. My own understanding is we're more like interglacial 11, which lasted a bit longer. So that's where I'd like to leave it. Don't worry too much about glaciers coming back, but make sure that we have a good strategy for dealing with them if they do show up, because you've seen how much energy it costs to stimulate a glacier growth. We don't have that kind of energy. If a meteorite comes and approaches Earth, we can send Bruce Willis and Clint Eastwood up and they'll explode it for us. But you've never seen a Hollywood film where a group of scientists stops a hurricane. A hurricane goes through about 10 to 20 megatons TNT of energy every 20 minutes. You can't stop a force of nature. You can't stop an earthquake. You can't stop a volcano. We just don't have the power. So think of a hurricane and then think of that times 1,000,000, and then you've got a glacier.
Well, we appreciate your expertise and your presentation. We hope that you will join us again soon on Climate Debrief.
Thank you for joining us on Climate Debrief. Executive producer is Angela Wheeler. Producers, Ethan Oddie and Scott Wheeler. You can find more episodes of Climate Debrief at co2coalition.org.